Energized.
Have you ever watched Star Trek and wished you could teleport instantly to another place? What if I told you quantum physics has actually brought that concept to life? Well, sort of. Today we're diving into one of the most mind-bending concepts in modern physics, quantum teleportation. We're not talking about teleporting people just yet, but scientists are teleporting particles, photons, atoms, even information across space using the strange rules of quantum mechanics. In this video, we'll explore what quantum teleportation really means, how it works, why it's not magic, and what it could mean for the future of communication, quantum computing, and maybe, just maybe, human teleportation. Before we get into the quantum part, let's talk about teleportation itself. In science fiction, teleportation usually means moving a physical object from one place to another instantly, without it crossing the space in between. You disappear here and reappear there. Sounds impossible, right? In classical physics, it is impossible, at least for now. But quantum mechanics, the theory that governs the behavior of tiny particles like electrons and photons, plays by different rules. Quantum teleportation isn't about moving matter. Instead, it's about transferring the state of a quantum particle, its exact configuration, to another particle far away without sending the particle itself. So how is that even possible? To understand quantum teleportation, we need to take a crash course in three strange quantum ideas: superposition, entanglement, and measurement. A quantum particle can exist in multiple states at once, for example, spinning both clockwise and counterclockwise at the same time, until it's measured. That's called superposition. It's like Schrödinger's cat, both alive and dead until you open the box. Now this is where things get weird. When two quantum particles become entangled, their properties become linked, no matter how far apart they are. Change one and the other responds instantly. Einstein called this spooky action at a distance. Measuring a quantum particle collapses its superposition. And if it's entangled, the act of measurement also affects its partner, instantly. These three ingredients, superposition, entanglement, and measurement, form the recipe for quantum teleportation. Alright, let's teleport something. Not a human, not a cat, but let's say a single photon, a particle of light. Let's call the photon we want to teleport photon A, and somewhere else we have two entangled photons, photon B and photon C. Photon B is with you, photon C is with your friend far away. Now here's the key. You perform a special Bell state measurement on photon A and photon B. This destroys photon A, you don't need it anymore, but it also transfers its state onto photon C, which is far away. But wait, there's a catch. You also need to send some classical information, 2 bits, to your friend, telling them the result of your measurement. Once they receive it, they can apply a specific transformation to photon C, and now, voila, photon C becomes identical to photon A, even though they never interacted. No matter or energy traveled between them, but the state was teleported instantly. So, what just happened? We didn't send the actual particle. We destroyed the original state and recreated it somewhere else. That's important. It means you can't clone quantum information. That's the no cloning theorem, a fundamental rule in quantum mechanics. It also means quantum teleportation isn't faster than light. Even though entanglement feels instant, you still need to send those 2 classical bits of information. That part can't go faster than light. So teleportation doesn't break physics, it just bends your mind. Quantum teleportation isn't just theory. It's been demonstrated in labs many times since the 1990s. In 1997, physicists in Innsbruck, Austria, teleported the state of a photon over a short distance in the lab. In 2015, scientists teleported quantum information between two diamonds at room temperature. In 2020, researchers at Caltech and Fermilab achieved long-distance teleportation over 44 kilometers of fiber optic cable with 90% accuracy. And in China, experiments have teleported quantum states from Earth to a satellite in orbit. These achievements are laying the groundwork for a future quantum internet. So what's the point? Why should we care about teleporting particles? Because quantum teleportation is key to building a quantum internet, a secure communication network based on the laws of quantum mechanics. In classical internet, data can be intercepted, but in quantum communication, eavesdropping destroys the message. That's why it's ultra-secure. Teleportation lets us transfer quantum information between nodes of a network without copying it, without interception. That could revolutionize cybersecurity, finance, and more. Quantum computers might one day be connected through quantum teleportation, making a powerful, ultra-secure global network. Let's go back to Star Trek. Could we ever teleport a human? Short answer: not anytime soon. To teleport a person, we'd need to scan and measure the quantum state of every atom in your body. That's roughly 10 to the power of 28 particles, and then recreate them exactly somewhere else. But measuring that much quantum data is impossible without destroying it, and we'd need an astronomical amount of classical data to transmit the results, more than exists in the world today. Also, philosophical questions arise. Would the teleported you still be you, or just a copy? Quantum teleportation sounds like science fiction, but it's very real. Scientists are doing it in labs. And while we're not teleporting people, we are teleporting quantum information, the most fundamental ingredient of reality. This is a peek into the future, a world where information moves without wires, where communication is unbreakable, and where physics itself allows for things we once thought were impossible. So next time you hear, "Beam me up, Scotty," remember, quantum teleportation is already here. It just needs a little more time before we can leave our atoms behind. If you enjoyed this deep dive into quantum teleportation, hit that like button, subscribe for more mind-blowing science content, and let me know in the comments. Would you ever want to teleport? Thanks for watching, and see you next time in the quantum realm.